Hello, everyone. Welcome to Dco Codes, and welcome back to our series on tackling the Project Euler refactors of my old Project Euler solutions. And just you know, trigger warning, as lots of people who have spent some time in the math arena, one way or the other. There's a lot of people that'll tell you, "Oh, it's Euler, it's Euler, it's Euler." It's always been Euler. Anyway, so the first problem we're going to approach is problem number 30. Fifth digit fifth powers. I don't know if I'm dyslexic, but that was interesting. Okay, and so the information is it's from 2002. Wow, that's a long time ago. And the difficulty rating is just 5% with just under 120,000 people having solved it. Okay, so you can read the sort of practice example they have here where they say, the sum of digits of power 4 of each digit, there's only so many numbers, right? There's a finite number, and then they sum together. The reason they sum together is just so that you have a single answer to shove in the box at the end, right? So they typically come up with these kind of ridiculous sums or whatever at the end of these problems so that whatever you put into the box is some string of numbers that really can't be guessed or brute forced in any capacity. So that's why they sum it. That's the sum part is pretty arbitrary. Really, the crux of the problem, right, is figuring out what the actual numbers are. And as you might suspect, the challenge. I mean, you can brute force it, just count up to 10,000, right, and you'll find all of them. But how do you know 10,000? That's the actual challenge of this problem. So now it says, find the sum of all the numbers that can be written as the sum of fifth powers of their digits. So it's the same problem as above here, but with fives instead of fours, right? And so if you look on the left here, I've got a bit of a write-up on how to approach this. It's all about determining your range of iteration, because you can solve all these problems just by coming up with some sort of brute force approach and just letting your program run for a day. You'll get the answer, but as you can see on the right here, that's really not the spirit of these Project Euler problems. You really want them to complete in under a minute. Now, that said, there are some sort of caveats to that, because as you'll see in this problem, the real work is done figuring out what the range of iteration is. So once you don't have to do that in real time. Like once you have the number, a good number that will have your brute force approach spit out a solution in under a minute, having it calculate that iteration range every time is not necessary, right? You have that number, so you use that number, and then the solution that utilizes that number takes less than a minute. That's okay. That's allowed. And so, extending that idea a little bit further, there are lots of problems that involve prime numbers. And, do you need to have an optimized prime number generator? Should you import NumPy or whatever whatever language you're using? Should you import a prime generator? And sure, why not? Right? There's some problems that involve permutations, and originally, as you'll see in the refactor series, I invented my own permutation generator, but itertools has one, I believe. I think it's itertools anyway, and Python, that would simplify that, right? So, at the time when I was learning, this is like 7 years ago, it was advantageous to make my own permutation or combinatorics generation function. But now, as someone who's been in the professional coding world for a little bit, it's obviously better to just use one that exists when you know where it is and how to use it, right? It's better to know how these functions work behind the scenes than to just start grabbing and using. But sometimes that's a luxury you don't always get to have. So anyway, the real thing about this problem is figuring out how to know your range of iteration, right? Find the sum of all numbers that can be written as the sum of fifth powers of their digits. Well, how high could that possibly be? So we have to figure out what the highest number is going to be before you can stop expecting solutions to come out of just iterating endlessly into infinity, right? There's got to be a termination point. And going back to what I said earlier about, you'll find sort of information that you can kind of just take with you and then craft a better solution. So in this case, we're figuring what the range of iteration is, and that kind of solves the problem for us. The actual calculation is not hard, right? Just going through the numbers and checking, like even if it were a million, that might take a few minutes, but you're in the right ballpark, right? To get all the numbers, that there's a termination point. And so we basically just need to sort of minimize that range of iterations so that whatever solution we have will execute under that 1 minute. And as we'll see, like the solution for this is not super difficult. Like I said, it's kind of just a brute force approach, but finding that range is what matters. So here we go. The greatest value of d to the power of 5 for the range for any digit 0 to 9, integer values, right, will obviously be d equals 9, right? So we know that d to the power of 5, where d equals 9, is going to be the biggest of all those possibilities. And so we can take that value, the biggest value possible, multiply it by the number of digits, and that'll determine the maximum number of digits in n at the upper limit. So like when I say n, that means we sum, right? This calculation here to determine n. And then we kind of work backwards. So you kind of treat it as two different sides of the equation. We treat one side like the actual digits to the power of 5 summed up, which is this. We're assuming they're all 9s at the moment. And then we're going to see what happens when we get the value of n and then compute backwards. We're going to take those digits and see what number we get. We're going to try and figure out, which side of the equation, the left-hand side or the right-hand side, is outpacing the other. And by doing that and kind of flipping around and playing with it, we're going to figure out where they kind of cross. Right? There's a plot that you can make of these two sort of sides of the equation, and sort of where they meet is going to tell you something about their relationship, right? So that's what we're doing here without the luxury of a plot. I can make a plot. I have a plot of some kind over here, I think. That's something later. Okay, so, if we had 7 digits, all 9s, and we performed our sum, to the power of 5 of each one, and then summing each digit, we only get less than half a million, right? So 7 digits of 9, when you compute the n value by summing up the fifth exponent of each, is lower than 9,999,999, which is all 7 9s, right? So we know that one side of the equation is well outpaced the other, right? So what we're talking about then, in this case, to be explicit, is we're saying we got 1, 2, 3, 4, 5, 6, 7 of these, and they lead to when you sum each of the digits to the 5th power, you only get this, right? That's insufficient, right? Because obviously this number is much bigger than this. So choosing an n value of that, when you compute the function on the maximum number of a 7-digit number, only yields a 6-digit number. So that we know that 7-digit numbers are probably off the table, or well, they are off the table. I mean, you can say probably if you want, because you're not feeling confident at this stage, but it looks good that we should expect no more values to show up somewhere around 6 digits. And so what we do is we assume, it's going to look a bit hand-wavy at first, but what we're doing is we're going to come up with an equation here. So this is our left-hand side, we'll say, right? And what we're doing is we're going to change the 9 to a d. We're going to leave that as a variable. We're going to say, okay, d to the power 5 times however many digits we have is going to equal to, and this summation over the range I from 0 to x, that is just a way to express a decimal number, right? So that's why the 10 is here. This is decimal, right? And the I determines which digit in the decimal number. And then we're assuming that all the values of d are the same still, right? And so that's why it's d times each digit summed up. So we can pull the d out. If you know your math, you pull the d out. You just sum that. That's 10 to the power of I on its own. But, I mean, knowing that, I kind of skip a step, so we can just explicitly do that. I'm not going to type it all out. But basically, we can pull this d here out of that, put it here. And now it's just d times the whole sum. Now, the next part is where your university or your college level mathematics start kicking in, or well, I guess you would have potentially learned some of this in high school. But the question is like, why would you take the derivative as opposed to just canceling out the d on both sides? And it has to do with like we're trying to get a sense of where the rates of change are actually the same, right? It's not so much where the values are the same, but we're saying that. What am I saying? Why do we take the derivative? That's a good question. You know what? I can't remember why we did that. But it is correct. I know that it's correct. I just can't remember why you wouldn't just cancel. But if you know your calculus, it basically changes things by a factor of 5, right? So instead of just canceling out a d and you get d to the 4 and canceling out this d on the other side here, actually I should update this so that it's matches. There we go. Right, and the d can't. You think the d cancels, but you're taking the derivative of both sides. And I should have put that in the parenthetical. And so we just rearrange and solve. Now we have to do a partial sum here. If you know your calculus, this is not a big deal. Basically, it just means that for any value of x, which determines the range of summation here, you can get the exact value based on another function, right? So this turns into a function. You can use that to get this function with a partial sum equation, basically. And so we just rearrange and solve. I don't recommend trying to solve for x because you have x in an exponent here and an x as a base here on the left-hand side. So you will not get a nice, pretty way to solve that. And because our range of values for d is integer values from 0 to 9, it's actually just fine to leave it in this form and just plug in values, try to kind of guess and check your way to integer values of d. It's not the best thing in the world, but you can do it. And you'll see that that's more or less what we do here. We've got the equation for d right here, which is the stuff in the floor, and we take the floor because we know it's going to be an integer value. And you can't round up an integer like that in this context, so we're not going to do that. And I happen to know that the range of iteration is fine to stop at 7, or terminating with the value of 6, because what this chart represents here, left column is x, and right column is the d, right? So I've actually I said, you can get your d values in one at a time if you want, because we know it's 0 to 9. But that's not what we want. I misspoke. I'm going to delete that. You can bet it. What we really want is we run through the values of x, right? And that tells us the average digit value. So for a 6-digit number, the average digit value would have to be 13 for the numbers, for the n on the left-hand side and the n on the right-hand side to be equal. So we know that the termination point is going to be in 5 digits, right? Because at some point between 5 digits and 6 digits, which you can't really do, you can't have half a digit, the average digit value exceeds 9, right? So once it's done that, you can't, in a base 10 system, you can't hope to achieve that. So that's how you know that it's going to terminate. So there we go. We know that it terminates somewhere around 5 digits. So that's basically our range of iteration. And what we can do for that is we can just assume that all the digits in the 6-digit number. Did I say 6 digits? Yeah, 6 digits is the maximum. Sorry. This is still a reasonable value. So we have to kind of account. What this means is that low 6-digit values will potentially work. Yeah, that's what that means. So we do have to kind of consider into the 6-digit territory, right? So we basically can assume then that all 6 digits as 9s what end value does that yield? That only yields 354,000. So we only have to go about a third of the way through the 6-digit numbers. And if you were to, figure out the actual calculation and run that many iterations, it's actually, I think it takes about 10 seconds, maybe 20, somewhere around 20 seconds on this particular machine. So it's under the minute mark already. But you can kind of take this further by, okay, well, if you assume not all nines, what if you assume 5 nines and, work one digit, the first digit as low as possible, right? Basically step it down and you get, for just under 300,000, you can get just under 300,000. And now you know that you're really close to the termination point. You could refine it a little bit to make it exact, but this actually runs in about, I think, 9 seconds when you use the actual solution. So that explains how you tune your range of iteration. Now, the next part of this series is going to be about refactoring these old solutions of mine. Now, Project Euler, they don't want you showing solutions, and I'm not going to show solutions, obviously, because I respect the heck out of these guys, and I love the site, and I want them to have good success, and we don't want a bunch of cheetahs. We don't want any cheetahs in this thing. We don't like cheating around here. We're gonna do it right. So, with that in mind, let me see what a solution. This is the original solution. As you can see, I did figure out the limit is correct. Okay, so what happens is we got the original n value of maximum. Like, we figured that out off camera. Didn't document it. Really dumb. Don't do that. That's a dumb thing to do. Don't know what happened there. That got double pasted. We're gonna kill that. But basically, this solution is pretty straightforward, although it's kind of silly looking. What it does is it collects all the numbers in this results variable that satisfy the conditions, and then it sums it after the fact. And the reason I did that, I suspect, is just so I could see the numbers come up, right? I just wanted to see it. So the question is, like, what does this look like, if you were to try to optimize it further? Because it can be, obviously. If you think about it, this is just, this is a sum too, right? That's what we do at the end here. We just sum it up. So we're going to get rid of that. We're just going to turn this into an actual sum. I wish I could see my cursor. That's really obnoxious. I don't know how to handle that in the moment. I'm just going to move on with my life here. And I don't know why there's no space there. I'm just going to space that. And then instead of that, we're just going to go total plus equals n. Yeah. There we go. But now, because of that, we can just go like this, actually, right? There's no point in having that. Sometimes there's a convenience to putting it on another line, but in this case, I don't believe that there is. So I think that should work, and I'm going to hopefully remember to blur out the answer. So there we go. I know that it's correct, or I think that it is. Let's put it in. Let's put it in. Hey. Oh, I solved the 40% in this account. So, Project Euler, they don't have, there's no money involved, right? So basically there's no incentive for them to be rigorous in some ways about recovering accounts, and I don't blame them. It's a nuisance, and people are really bad with their own passwords, So at some point, I lost track of my original account. So I have all these solutions, but I have no track record of them. So I'm going to go through them. I'm going to refactor them. I'm going to make them faster and better. Make sure that they all stick to the 1 minute time, and then I'm going to put them in to see if they're correct, and sort of create a new account with my old solutions, and we'll see if they're correct or not. So this is a decent enough solution. I have a slightly modified version that's timed. So let's see. The original one is right here, and we'll time it real quick and see. It should take, I think it takes about 16 seconds, depending on how jacked my computer is. 16 and a half seconds, go. All right, so, and then I've got the loop one. This is more or less the same, yeah. So the only difference really is I use that max n file with the constant and the digit powers all calculated. You may have noticed, actually, I should mention this real quick, that there was a very sort of sloppy thing done here, right here, still, I haven't fixed. There's only 10 digits, so you can just compute them in advance, right? For every digit, and that's what I do actually right here at the top. Right, I just make a dict of all the values, just a mapping, from one digit to the fifth power of its value. So, and that way it doesn't have to do it every time it gets a new digit for every friggin' number, right? And surprisingly, that doesn't actually, I don't think that saves as much time as you would think it does, which is actually funny. So there might be some caching that's going on that's sort of saving my butt there. So this is a full comprehension. So this is if you just treat everything as sums, right? You've computed the digit powers in advance. You've got the good max end value here. I didn't even bother importing it. This is sort of like as optimized as you're going to get, basically. And I think this is about 10 seconds. So, with the reduced value of iteration, and with the computing the digits in advance and using, in this case, a double list comprehension, one for this sum on the right and one for the overall sum, we can actually get this solution down to about, what was that, 2/3 of its original duration. So that's pretty good. And yeah, I think that's how it's going to go from here. So I'm going to go edit this video. And thanks for sticking it out and joining me for the Project Euler series. Have a great day.